In this video, we will look into the meaning of atomic and molecular term symbols, how to develop them, and how they relate to spectroscopy. It is first important to realize that all energy is quantized. That means any motion of an electron or a particle, be it motion in space and translational motion, the vibration of a bond, the rotation of a molecule in free space, or the transition of an electron, can only change by set amounts. As you learned in freshman chemistry, 4 quantum numbers define the behavior of an electron in a hydrogen-like orbital. Unlike freshman chemistry, where you learn to read the periodic table, atoms are only actually an approximation formed by linear combinations of hydrogen-like orbitals. For example, you learned carbon to be 1s2, 2s2, 2p2 as the 6th element on the periodic table. In actuality, carbon is a linear combination of 6 hydrogen atoms added together into one function. Similarly, molecules are approximated by linear combinations of atomic orbitals to form molecular orbitals. Therefore, the entire energy of the atom is quantized in an atomic term, since each individual component is quantized. And since the molecule is built from atoms, which were built from single electrons, which are quantized, the energy of the entire molecule is quantized, and this can be expressed as a single term. With regards to spectroscopy, it is important to remember that allowed transitions only occur because of the absorption of photons of radiation. Since a photon is a fermion with a spin of 1, all transitions are limited to quantum changes of 0, +1, or -1. We'll start with a review of atomic quantum numbers. As you may recall from freshman chemistry again, the electrons in a hydrogen-like orbital are defined by 4 quantum numbers. The first number, n, your energy level, can have any integer value greater than 0, and its meaning is the shell of that electron, or the level it's in, or the row on the periodic table. The second number, L, is the magnitude of the angular momentum of the electron. This is related to the level that the electron is in, and it can have any value from 0 to n-1, and defines the orbit. For example, L equals 0 is an s orbit, L equals 1 is a p orbit, L equals 2 is a d orbit, L equals 3 is an f orbit. The third quantum number, m subscript L, or m sub L, is the relationship between the angular momentum of the electron and its relationship to the z-axis, which is the reference axis. This, in turn, is related to the previous quantum number, as it can have any value from -1 to +1, and indicates the orbitals or suborbits that are present. For example, for a p orbit where L equals 1, m sub L can have the values of -1, 0, or +1. Therefore, the p orbit has 3 sublevels, or 3 orbitals, and can hold 6 electrons. The final quantum number, m sub s, which can have a value of +0.5 or -0.5, represents the spin of an electron, either clockwise or counterclockwise. By Hund's rules, This limits each orbital to only 2 electrons, and the Pauli exclusion principle applies. Now, to build all the electrons into an atomic term, it's simply a matter of translating the electronic quantum numbers. In this case, the energy level of an individual electron does not matter, since the sum is the only thing that matters. The angular momentum, which for an individual electron is a lowercase l, in an atom is symbolized by an uppercase L, which is determined by any value from 0 up to and including the absolute value of all of the sums of the m sub l's, or all of the angular momentums of all the electrons. This defines the term. For example, for an atom, a lowercase l equals 0 was a lowercase s orbit. For an atom, a capital L of 0 is a capital S term. For an electron, a lowercase 1 was a lowercase p orbit. For an atom, an uppercase L of 1 is a p term. An uppercase L of 2 is a d term. 3 is an f term. Beyond this, the follows progressively. If L equals 4 would be a G, L equals 5 would be an H, I, J, K, and M. The individual angular momentums as relative to the z-axis do not count, but spin is still important. A capital S represents all of the possible values of all of the electrons arranged so that their sums would equal anything from 0 up to and including the sum of all of the individual electrons. This is the total spin of the atom. Since spin and orbit both have angular momentum, an atom has an additional term, the quantum number J, which is equal to the total angular momentum, or L, of the electrons, plus the total spin of the electrons, S. This is called spin-orbit coupling and represents the net torque exhibited upon the individual atom. So to consider an atomic term, in the center of the term is the sum of the angular momentum of the electrons, capital L. This is calculated, again, as any combination between 0 up to and including the sum of all the m sub l's of the electrons in the molecule, of the atom, rather, and this is your term. In the upper left-hand corner, 2s plus 1 is called the spin multiplicity, where the value of s is obviously multiplied by 2 and added to 1. This is the degeneracy of each term. For example, an atom with one unpaired electron would have a spin of a half and a multiplicity of 2. This would indicate that that electron could either be up or down in 2 degenerate states. And in the lower right-hand corner is the value of J, the spin-orbit coupling, as L plus S. The ground state of any individual atom within the range of all the possible L values is determined as follows. This method follows Hund's rules, which state the term with the maximum multiplicity, the maximum 2s plus 1 value, is the lowest energy state. Should 2 or more states have the same multiplicity, the term with the largest value of L, angular momentum, is the ground state. And if there are 2 or more states with the same L and the same S, and an atom with a half-filled shell, the lowest value of J determines where the ground state of the electron should be. These rules lead to an allowed transition. Bearing in mind once again that the absorption of a photon of light means imparting an angular momentum change of 0 plus or minus 1. These are called selection rules. Therefore, again, based on the selection rules and based on the spin of a photon, the total term, the angular momentum, can only change by 0 plus or minus 1. Since electrons have spin values of a half and are bosons, they cannot absorb a photon. Therefore, delta S has to be 0. And finally, since J equals L plus S and S has to be 0, an allowed transition can only have a delta J of 0 plus or minus 1. We will now go through a couple of examples of how to construct an atomic term symbol. We'll start with boron, which has an electron configuration of helium 2s2 2p1. First, we start by putting the orbitals in their proper locations, starting with the 2s level on the bottom and the 3p orbitals on top. Remembering, the 2s level has an m sub L of 0. The 2p level can have an m sub L value of minus 1, plus 1, or 0. The electrons are entered according to the Aufbau principle from the bottom to the top, and bearing in mind that no orbital can have more than 2 electrons. In this configuration, if you add up the angular momentum of each electron, you have L equals 0, plus 0, plus 1 for an L value of 1, which gives rise to a p state. Again, adding up the spins, plus 1/2 for an arrow up, minus 1/2 for an arrow down, and plus 1/2 for another arrow up, gives you a total spin of 1/2. This gives rise to a spin multiplicity of 2. By calculating L plus S, 1 plus 1/2, one gets 3/2 for the value of J, which is commonly denoted as a fraction, giving a final term of 2p 3/2 for boron. Moving on, oxygen, which has a ground state configuration of helium 2s2 2p4. We once again start by putting all the orbitals in their proper location, with the 2s level on the bottom, the 2p level on top, where the 2s level has an m sub L of 0, the 2p level has values of 1, minus 1, and 0. And again, adding the electrons properly, with no orbital having more than 2, and nobody having 2 until everybody has 1, we find oxygen has 2 unpaired electrons. Adding up the m sub L values of 0 plus 0, plus 1, plus 1, plus 0, minus 1, gives a total L of 1 as an absolute value, and again gives rise to a p state. Adding up the spins, plus 1/2, minus 1/2, plus 1/2, minus 1/2, plus 1/2, plus 1/2, gives a total spin value of 1, and a spin multiplicity and a degeneracy of 3. Finally, adding up L plus S gives a J value of 2, and a final term of 3p2. For one more example, we can start with fluorine, which has an electron configuration of helium 2s2 2p5. Again, adding the orbitals in their proper places, starting with the 2s on the bottom and the 2p on top, where the 2s has an m sub L of 0, 2p has m sub L values of 1, minus 1, and 0 for the 2p z-axis. And once again, Inserting the electrons one at a time so that no orbital contains more than two, one finds that fluorine also has one unpaired electron. The total of the m sub L values for each electron's absolute value is 1, where once again we have a p state. There is one unpaired electron, so that gives an s value of 1/2, which again gives a j value, L plus s, of 3/2. And one's final term for fluorine is 3p 3/2. Now that we've seen how individual electrons in their orbitals make up an atomic term, it's time to look into how these same electrons can combine as atoms come together to form a molecule. Molecular orbitals are formed by linear combinations of atomic orbitals. There are two linear functions, addition and subtraction. Therefore, each pair of atomic orbitals forms a pair of molecular orbitals, or MOs. The lower energy MO is called the bonding orbital. The higher energy MO, signified by a star superscript, is the antibonding orbital. Angular momentum is conserved when forming molecular orbitals. This means atomic orbitals with m sub L of 1 will only bond with other atomic orbitals of m sub L equals to 1 to form what is called a lambda equals 1 pi orbital. M sub L equals 1 can come from any of the atomic orbitals. P levels, D levels, and F levels all have the value of m sub L equals 1, but these will still only form pi molecular orbitals. The z-axis, m sub L equals 0, is still used as the reference axis in the molecule. Even simple diatomic molecules are complicated. They have two different patterns of molecular orbitals. The cutoff for these patterns is a molecular weight of 7 and is based upon the electronegativity of the elements. Multi-atomic molecules are linear combinations of linear combinations. Therefore, for example, in methane with 4 hydrogens and 1 carbon, the 4 hydrogens are first combined into one function, and then that function is combined with the carbon. The energy of each individual electron is still quantized when atomic orbitals are combined to form molecular orbitals. As you will see, the difference between these values is simply the matter of the difference between switching from Roman letters to Greek letters. For example, your principal quantum number n still exists. It still denotes the energy level of the electron, and it can still have any integer value greater than 0. However, in the case of a molecule, the only electrons which contribute to the bonding are those in the valence shell of each individual atom. Therefore, n values from the lower shells, the closed shells, do not appear. Instead of L for the next quantum number, we have the Greek letter lambda. This still signifies the magnitude of the angular momentum. It can still have any value from 0 to n minus 1, and it now denotes the molecular orbit. As mentioned, the only difference is Roman numbers and letters get changed to Greek letters. So instead of an s equals 0, one has a lambda equals 0, producing instead of an s orbit, a sigma orbit. When lambda equals 1, one gets a pi orbit, which is the Greek equivalent of p. For lambda equals 2, a delta orbit, or the Greek letter for d. For lambda equals 3, a phi orbit. M sub lambda now tells you the direction of the angular momentum of each individual electron, and this can have values ranging from minus lambda to positive lambda. In addition, the electrons still have spin, and those values can be plus a half or minus a half, denoting the spin state of the electron. Just as in an atom, the sum total of all the contributions of all the electrons in a molecule get combined in what is called a term. Again, the energy levels of the electrons are not significant in the term. The quantum number, instead of a capital L, is now a capital lambda to describe the term. This can have all values from 0 up to and including the absolute value of m sub lambda. And this defines, as I said, the term of the molecule, where a capital lambda of 0 provides with a sigma state, where a capital sigma is the equivalent of a capital S. A capital value, lambda of 1, provides a pi term. A capital lambda of 2 gives a capital delta term. A lambda value of 3 gives rise to a capital phi term. Spin is also summed up within the term for the molecule, where capital lambda is the sum of everything from 0 up to and including the absolute value of the sum of all the m sub lambdas, and that is the total spin of the molecule. Instead of a J term, for a molecule, one has an omega term. This term is still L plus S, or capital lambda plus capital sigma, and indicates the spin-orbit coupling, or the net torque that the electrons force upon the entire molecule. Just like all of the electrons in an atom add up to the atomic term, all the electrons in a molecule will add up to a molecular term. In this case, the term symbol is directly derived from the atomic term symbol, with Greek letters replacing Roman letters. For example, in the middle is now the capital lambda. This still is the term of the molecule, and it's the total possible angular momentum values for all the electrons from 0 up to and including m sub L. In the upper left-hand corner, instead of 2s plus 1, there is now a 2 sigma plus 1, which signifies the spin multiplicity or the degeneracy of each term. Again, in the lower right-hand corner, instead of a J, there is now a capital omega. This is the spin-orbit coupling of each term and the electrons that contribute to it. Just as in an atom, the ground state of a molecule can be determined once again by following Hund's rules. The first rule states still the term with the maximum spin multiplicity is the lowest energy state. The second term is still, for a given multiplicity, the term with the largest lambda now is the ground state. And in atoms with half-filled shells, the value with the lowest omega determines the ground state. These selection rules, these term symbols rather, tell you the allowed transitions for the molecule, as determined by selection rules, where once again, since you are absorbing a photon, which is a fermion with a spin of 1, only a change in angular momentum of 1 is acceptable. So a delta lambda can be 0, plus 1, or minus 1. However, spin cannot change, so delta sigma has to be 0. And since omega depends upon sigma plus lambda, the change in sigma is also 0 plus or minus 1. Now let us look to see how we can construct a molecular orbital diagram and derive a term symbol for a molecule, starting with the molecular orbital diagram of a low molecular weight compound, B2. We have already seen what the electron configuration of each individual boron is. As mentioned previously, angular momentum has to be conserved when forming molecular orbitals. Therefore, all the lambda equals 0 orbitals will meet to form other lambda equals 0 orbitals, which will be sigma and sigma star. Also, all of the m sub l equals 1 will form lambda equals 1 orbitals, which become pi and pi star. It's worth noting that in the transition from atomic orbitals to molecular orbitals, the relationship between the angular momentum and the z-axis is still important. For example, the pi orbitals have m sub lambdas equal 1 and m sub lambdas equal minus 1. We now start entering electrons one at a time in each orbital, starting from the highest to the lowest. You find in the final configuration that the B2 molecule has 2 unpaired electrons. However, one of these is in an m lambda equals 1, and the other is in m lambda equals minus 1. Therefore, capital lambda is 0, and we have a sigma term. The 2 unpaired electrons give a total spin of 1, or a lambda of 1, and therefore 2 times 1 plus 1 gives a multiplicity of 3. 3 plus 0 gives an omega of 3, so the simple term symbol for B2 is 3 sigma 3. We will now move on to build a molecular orbital diagram for a linear molecule that's made from elements with a higher molecular weight and greater electronegativity. You've already seen the electron configurations of oxygen and fluorine. We will now build the OF molecule, where once again, with angular momentum being conserved, everything from an m sub l equals 0 state forms a lambda equals 0 state, which is sigma and sigma star. Similarly, everything from an m sub l of 1 forms an m sub lambda of 1, and these orbitals become pi and pi star. Once again, the relative relation to the z-axis is still important, so the pi orbitals are labeled m sub lambda of minus 1 and m sub lambda of plus 1. Additionally, you will note by looking at this diagram that the orbitals are arranged differently. In a low molecular weight compound, the upper sigma orbital is at a higher level than the pi orbitals. However, as molecules get heavier and electronegativity plays a part in it, the sigma orbital formed from the m sub l equals 0 p orbitals now lies at a lower state than the pi orbitals. We now start putting the electrons in, again, one at a time, from the lowest orbital to the higher orbital. You will see in this case that I have one unpaired electron, and that electron is in an m sub lambda of minus 1, which gives a capital lambda of 1, generating a pi term. Also, the one unpaired electron gives a total spin of a half, sigma equals a half, where 2 sigma plus 1 means that this term is doubly degenerate. 1 plus a half gives you 3 halves for omega, making the final term a 2 pi 3 halves. We now have to go into a deeper understanding of the molecular term and the nature of the molecular structure and bonding. First of all, if you recall, molecular orbitals are linear combinations of atomic orbitals. These atomic orbitals themselves are linear combinations of hydrogen-like orbitals. The hydrogen-like orbitals are the solutions to the fundamental wave equation and the Schrödinger equation. Therefore, It is important to remember that these mathematical solutions both define the reality we live in and also carry consequences with them. A deeper look at this fact is a deeper look at the math. Since these are functions at their very basis, they have both symmetry and parity. What are commonly called orbitals are actually graphs of probability density functions, which, if you recall, is the integral of the psi squared. If a function is normalized, that integral over all space should be 1. Math functions exhibit both symmetry and parity, which at first glance might seem to be identical, but there's a crucial difference. Functions have symmetry based on how they behave upon inversion through a center. A function is even, or gerade in German, symbolized by a G, if it retains both its shape and its sign upon inversion. A function is odd, ungerade in German, symbolized by a lowercase u, retains shape but not sign upon inversion. Symmetry is a binary option. Something is either symmetric or asymmetric. On the other hand, functions have parity based upon how they behave upon exchange of variables. A function has positive parity if it is unaffected by the change. For example, the function x squared. 2 squared is 4. Minus 2 squared is also 4. So therefore, x squared has parity. On the other hand, a function has negative parity if it is affected by exchange. It is easy to see that for the identity, 2 is not equal to minus 2, so f of x is not equal to minus x, and therefore that function has negative parity. What may seem to be a mathematical obscurity actually has consequences in the real world. Symmetry and parity are degenerate, and they play no role in the physical behavior of an atom. What that means can be seen by example. For example, if one takes a hydrogen s orbital, this is spherical and has a positive sign. It also has a center of symmetry. When this function is inverted, one finds that one gets back the original function. Therefore, the s orbit is gerade. The mirror image is identical to the original, and it also has positive parity, as changing the variables from one side to the other does not change the outcome. On the other hand, if one was to look at a hydrogen-like p orbital, as you recall, the p orbital has 2 lobes. One of them is in the positive range, one of them is in the negative range. This shape also has a center of symmetry as far as shape is concerned. However, when the p orbital is inverted, you will notice the shape is retained, but the sign changes. Therefore, in terms of symmetry, the p orbital is ungerade, or odd, because the mirror image is the opposite of the original image. It also has negative parity because exchanging variables cause the outcome of the equation to change. When one looks at molecular orbitals, however, one finds that the link between symmetry and parity is removed. One has to recall that molecular orbitals are linear combinations of functions. Since these functions are not necessarily identical, there is no longer degeneracy between symmetry and parity. For example, if one takes the oblong sigma orbital and the corresponding sigma star orbital, one finds that the sigma orbital has the same sign, sigma star has opposite signs, yet both retain a center of symmetry. When these functions are inverted, one finds that the sigma orbital remains identical, and the sigma star orbital changes signs. Therefore, for the sigma orbital, it has gerade or even symmetry and positive parity. For the sigma star orbital, one sees uneven or Ungerad symmetry and negative parity. This situation is the same as is found for atomic orbitals. As one goes further and one looks at the next lambda equals 1 pi systems, you have the pi and the corresponding pi star orbitals. These exist in two different planes and have positive and negative signs, yet you will note that both have centers of symmetry. Upon inversion, the inverted pi orbital, and here you have the inverted pi star orbital. Upon examination, you find for the pi orbital that I have uneven or Ungerad symmetry, yet from left to right I still have positive parity. Each lobe is both positive on top and each lobe is negative on the bottom. For the sigma star orbital, I have even symmetry. Yet, as the sign changes from left to right, I now have negative parity. This case is the opposite of what is found in atomic orbitals, so symmetry and parity are no longer connected when you form a molecule. We will now see how this separation of symmetry and parity affects reality. We'll take another look at the full term symbol for the molecule B2. We have already done this term symbol, and therefore you will recall that we already know the electron configuration of the two boron atoms involved. We also know that anything with an m sub L of 0 is going to combine to form sigma and sigma star orbitals, both from m sub L equals 0 from the 2s and the 2pz. Also, anything with an m sub L of equal to 1 will form a lambda equals 1 or a pi orbital. These are, once again, bonding and anti-bonding pi and pi star, and return the relationships of the z-axis with m sub lambda equal to 0, equal to 1 or minus 1. And we also know how the electrons fill this symbol. Therefore, from looking at the term rather, we find once again that lambda is 0 because one electron is in a pi m sub lambda 1 and the other electron is in a pi m sub lambda 2. Therefore, we have a sigma term. As there are two unshared electrons, the total spin, lambda, is going to be equal to 1. And you will have a triple degeneracy of 3, 2s plus 1. Similarly, the omega value of lambda plus 0 is again going to be 1. Now there are different things to look at in the term also. You will note once again that both unpaired electrons are on pi orbitals. If you recall from the previous few minutes, pi orbitals are uneven or Ungerad, therefore the entire molecule is going to be Ungerad. Additionally, pi orbitals have positive parity, therefore this molecule will have positive parity. And this is the entire term. We will now see how the differences between symmetry and parity will affect the term of the molecule OF. As you know, this is a molecule we've already done where we've seen the electron configurations of both O and the F atom. And once again, how these combined with m sub L's equal to 0, combining to form sigma orbitals, m sub L's equal to 1, combining to form pi orbitals, each case with a bonding and anti-bonding site, and in all cases with the m sub lambdas, the relationship to the z-axis being a plus 1 or a minus 1 on the pi and pi star axes. Looking at the electron configuration, with one unpaired electron, you can see lambda is still equal to 1, therefore the term is a pi. Also, with one unpaired electron, sigma is 1/2, leading to a spin multiplicity of 2, and 1 plus 1/2 leads to an omega spin-orbit coupling of 3/2. In this case, your lone electron is occupying a pi orbital, a pi star orbital rather, and pi star orbitals are even, therefore the term is even or subscripted G. However, a pi star orbital also has negative parity, so the entire term for the symbol for the molecule OF, it's a 2 pi 3/2 G minus. We'll now see how symmetry and parity affect spectroscopic selection rules. For an allowed transition, you still have the fact that the change in total angular momentum, delta lambda, must be 0, +1, or -1, because, again, you're absorbing photons which have a spin of 1. Delta sigma, the spin, has to be 0 because electrons have a spin of 1/2, and therefore delta omega, lambda plus sigma, also can only be 0, plus or -1. Photons have other properties besides spin, however. On the one hand, photons do have parity. Therefore, parity must be conserved. This means that a plus state to a plus state or a minus state to a minus state are allowed, but a plus state to a minus state is never allowed. On the other hand, since photons have negligible mass or form, symmetry does not exist. For any transition to happen, there must be some change. Since the change is not offset by a change in the photon, you find that symmetry must invert. Therefore, even to odd, G to U, is allowed, but no transitions from G to G or from U to U are allowed.